And then you have forces coming from the link on that, and then you have force coming from the wall, and there was no gravity, so it was full FPD. But pay attention, in fact, if you look at it, there is an atmosphere around this. We are not living in a vacuum, we are living in a pressurized environment. That means there is a P0 everywhere. And that P0 is acting right here, right? So that P0 is here. That means what? That means that P0 was here, and there was another one here. So what happens to these P0s that are everywhere?
You cancel out.
I didn't write it on FPD because they cancel out. Right? So what I solved for that in the previous class was I solved for only P because they will cancel out, they were canceling out, and it just makes your FPD very messy, right? But look, if I get my P and I want to get the state of this gas, so I go to equation of state, and equation of state say P is equal to rho RT. What kind of P should I put there? Absolute value, absolute pressure. That means the sum of all the pressure, because it is the absolute value Kelvin. It's not a Fahrenheit, it's not relative to a different, it's just absolute temperature. So it's an absolute pressure, absolute temperature. So when I put absolute, I have to add this to the actual, the red pressure to get the total pressure. That's the reason I have to do that. Good? Now we're back to the last point, which was the shear stress, and we talked about Newtonian, non-Newtonian fluids. And I want to expand that section a little bit more, and then we solve some problems. There's going to be a waiver again, meter waiver today, and then we watch a few videos. So back to shear stress. Then, if the relation between shear stress and velocity is linear, u dy dx, du dy, so u is velocity and y is the direction orthogonal to the direction of flow, right? In that case, we would say this is a Newtonian fluid. Any other relation between shear stress and velocity is velocity. Obviously, you have a relation between gradient velocity, not velocity itself. Any relation that is not similar to that is called non-Newtonian fluid. And this notation of linearized relation between shear stress and velocity makes this problem solving very easy compared to non-Newtonian when you have a nonlinear relation. So in fact, if I want to visualize that, if I want to, let's say you have a channel like this, and this is the wall. This is a solid wall. And let's say the flow is going here, this direction. So we know that the fluid, based on the first class, the definition, it cannot resist its own shear stress, right? So it moves. So if you leave it on the surface, it will move, and then you can also say that if you add pressure, it will move to the right. That's the entire thing with pump work. They add a pressure difference and they cause the velocity to move. So this velocity of the fluid, right, is moving between these two enclosure. And let's say I bring the top surface, so let's say this distance, call it d. Let's say I bring the top enclosure very, very close to the surface, to the wall, very, very close, tens of millimeters, hundreds of millimeters. In that case, you see that if the velocity is going linearly like that, the fluid is Newtonian. So what's the velocity at the wall? If I be able to zoom infinite times, we discussed in last class, the velocity at the wall is 0. And the velocity at the top surface, because I'm kind of, with my hand, I'm moving this top surface. Let's say this is a metal sheet, right? Metal sheet. And I use either a roller or my hand to push it to the right. So let's say this top sheet is moving with velocity v, but the wall is 0. So if I have a microscope that I can zoom infinite times on this here, what's the velocity here? Always?
0.
0. So velocity here, let's call it u. And let's say this is your y direction, right? So u at y is equal to 0 is what? 0. What about u at y here, which is, call it this value, call it delta. What about u at delta? Y is equal to delta.
It's equal to the velocity of the metal sheet.
Exactly. Why? Because the tiny molecule of that fluid will stick. If you go infinite time molecular level zooming with a microscope, you see that they are just stuck on this surface. So the velocity at y is equal to delta is equal to capital V. So we mentioned last class there is going to be a profile because you see versus u versus y is not constant, it's varying. And I mentioned if I bring these two sheets very, very close together, that this profile is going to be a line, and this is called Newtonian fluid. Now you can see that for that, you can see the basis for this relation. This is the basis, the entire physical observation and basis for that relation. In that case, I can write tau is equal to dynamic viscosity mu times the velocity difference. Look at the equation of this line. What's the velocity at uy plus delta v minus the velocity, this is delta, right? You can write it delta u over delta y, right? Can't you do that? You can. So delta u is the velocity here, which is v, capital V, minus the velocity here at y0 is what? 0 divided by delta y. The y here is what? Delta minus y at the wall is 0. So we can approximate that mu v over delta. That's the shear. And what is that shear? That's the shear that you need to pull this metal sheet to the right. So if I ask you to find the value of force that is required to push that metal sheet to the right, before you compute it, you go to the actual intuition and say, if I go to the lab and create that metal sheet and put it on the fluid and bring it very, very close to the surface and do that, obviously I get some force. I have to apply some force, otherwise it's not going to move. Just like a block, if you put it on an incline, let's say you lubricate the surface of incline and you put a block there, what happens? It's going to move down, and the more lubrication you have, the better lubrication is slide faster, right? So if I ask you, find the value of force required to move this plate, can you compute it? You use the definition of the stress. What was the definition of the stress? In the mechanics of material, you had normal stress. So let me write this element here. If this was an element of fluid, element of whatever material, solid, fluid, doesn't matter, continuum material. If you take an element, the tiny element here in the fluid, you have normal stress in Y, normal stress in X, and then you have shear stress, tau xy. Tau xy in the xy plane, right? Sigma x, sigma y. We discussed that. So in mechanics of material, we talked about the normal stress. We saw a problem. We also talked about shear stress. Here in the fluid, what is my normal stress? Do I have normal stress? Let's say you have fluid in a tank, in equilibrium.
The weight of whatever the tank
Yeah.
is.
So if you go down to the bottom of the tank, you see that you feel, if you swim there, you see that your ear gets started and you feel pain. It's the pressure. So in this normal stress, these are pressures, right? These are pressures. What about shear stress? If the fluid is in equilibrium, what's the shear stress? 0. But when it moves, because those things are sliding with each other, you can see that there's going to be some friction. So there is a shear field, and it's different in every point in the field. We'll talk about it in the video. And depending how your fluid is moving, so if the fluid is moving in a laminar way, that means you have laminates that they are just rolling on top of each other. It's called laminar flow. But if the fluid becomes chaotic and all those particles they hit each other, they move in a chaotic, we call it turbulent flow. And the shear stress will increase. This is completely intuitive, right? You can see that, well, if there was so much perturbation, the shear stress is increasing, right? So we talked about it in the video, but for right now, let's say this is completely laminar. That means everything is laminated and nice. The question is, how much force do I need to push this to the right? Well, we use the definition of stress. What was the definition of the stress? The stress was any kind of the stress was what? Force divided by that area that force acting on. Only the area that force is acting on. Right? So look at here. If I draw that in 3D, it's going to be like that. That's your plate. You see that? So that's your plate, and that's your hand, and you're trying to move it to the right. You see that? So every element on the surface of that, look, if you cut it up into tiny parts, you see that? On each one of those, if you draw a 3D, you have some resistance from fluid, right? dF, the delta force resistance from fluid. If you don't have fluid, it just goes right. But the flow is resistant. So how can you find that? Well, you can use the definition of the stress. You say that force, right? dF is equal to, force is equal to the stress times area, right? So what is my force? dF. You see, a tiny infinitesimal force, the resistant force coming on each element is equal to what? The stress. What kind of a stress caused that force? Is it the normal stress, the pressure? What kind of a stress causes resistance? Is it a normal stress? It's not. It's a shear stress. So you say tau times area. What's the area of this infinitesimal element? Did you have calculus too? Do you remember dA? You did integral?
It's really small.
Yeah, it's very small. So you can say dA, infinitesimal area. So you can write it tau times dA. Or alternatively, you can say shear is equal to dF over dA. These are exactly the same. All I did, I just rearranged the equation. Now, back to the main question, how can I find the force? Should I find the force on one of those infinitesimal elements only? What should I do? If I find?
Do it over the course of it.
Yeah, you see, forget about this direction, because we are only talking about the surface, the top. What should I do to find the entire force on this plate?
Multiply by the area.
Yeah, to add, or other word, you add all this infinitesimal together, so you in fact integrate all those little things, all those little parts, you add it together. What's the addition when you go to infinite? It's called integration. So the total force is what? The force, the resultant force, integral of tau dA, right? And because it's a surface integral, they sometimes put double integral like that. If you have volume integral, how many integral they put? 3, right? Like that. But here you have double integral. That means integral over surface, tau times dA. Now, as he said, Tau is constant everywhere on that surface. I can take it out of integral. Why? Because it just can't. Tau will only depend on the velocity gradient. It's just similar everywhere on this plate. You see that? So you can take it out. So it becomes what? Tau times integral of dA. What's the integral of dA? The area of that plate. So it's going to be what? Tau times A. So in this case, if I want to find that force, we're getting closer to integrate. Pay attention. If I want to find that force, what should I write here? F is equal to, what's the value of my tau? The value of my tau is what? Mu V over delta times the area of this plate. Let's call it A. The entire plate's area is A times A. That's it. Now, one question we always had whenever we studied other courses, they usually encounter, especially in thermodynamics, it's called dynamic viscosity mu. One way is how can we measure it in the lab? There are different ways to do that, measure. One way is to set up that device so you bring the surface very close, so this order of 0.1 millimeter, very, very close, you don't even see the eye. And then you have some sort of metal sheet that is rolling on this, and you can measure both velocity. So in fact, you give the machine the velocity, and you can measure the force. It's transducer. So you have the force, you measure the velocity, you have the distance, and you have the area of metal sheet. So what do you need? The only remaining thing is viscosity. You can compute it. So in fact, you can compute the viscosity in the lab using the same experimental setup. But look, for that, you need to make a huge metal sheet, and it's not accurate. Why? You see that distance is not going to be always 0.1 millimeters. Sometimes, because the sheet is big, in the middle of where you have twists or they go up and down. So this is not a good way of measuring that. This is not a good way of measuring that. There's not another way to do that. Another way is to make a rotating cylinder. I want to show it here. So let's say I have this cylinder, right? And this is an enclosure. So it is inside another cylinder, as you can see. There you go. So the outer cylinder is rotating with a constant omega, with a constant angular rotation. And the inside cylinder is fixed and is connected to a torque measure. So this is very practical. You see it in the lab. We have things like that. So the inside cylinder is fixed. The outside cylinder is rotating. So that's connected to some sort of gearbox and motor. So it's rotating with angular velocity. And the inside cylinder is fixed, but it's connected to torque measure. Now, if I put a fluid between them, what happens? If I don't have a fluid between them, I can easily rotate the outer, right? This outer cylinder. There's not going to be any torque on the inner cylinder if I don't have any fluid. Let's say vacuum. If air is even fluid, so if you have air, still you see a little bit tiny torque on the inner cylinder. Let's say I have some fluid here, now filled between these two. So everywhere between these two is filled with fluid. Do you see that? And I want to find a relation between the torque and viscosity of that fluid. How can I do that? I know that this setup is more promising than the other one. Why? Because you can have a tiny cylinder instead of large, huge metal sheet. And for the metal sheet, you can't have a constant velocity forever, because at some point you come to the end, right? But this cylinder can have forever, and it's symmetric and it's easy to build. So this is completely promising. So if you can find a relation between the torque, because this is what I can measure. I put a sensor, I can measure that, right? I can measure the torque and I can measure all the dimension. Now, what's the relation between that torque and omega and the dimension of this plate, and between that and viscosity? We want to work on that. Now, to find that relation, again, we can use this Newtonian, assuming it's Newtonian, right? We can use the same thing with it here. So all I need to do is to find the gradient of velocity if the distance between two plates is small. So that's what I want to do right now. So let's say the outer diameter is RO, the inner diameter is RI, and let's say this height is H. I can build it, right? I can measure it. These are all the information I have. And let's say the fluid between these two is Newtonian. That means I can apply this relation, right? So that means the tau, the assumption tau is mu du dy. Okay, in order to solve this problem, I know that you see in the z direction, I don't have like any kind of change in the flow field, but if I look it from the top, so if I look it from here, if I look it from the top, I do actually see two concentrated circles like that. And this guy, the outer one, is rotating with omega, and the inner one is fixed, right? So what happens? This is the fluid. Let's use blue, because I use blue. So the fluid is here, right, between these two. It can be fluid, gas, anything that is Newtonian. And this is fixed, omega is 0. So what happens? If this distance is huge, right, then you have you know that the velocity is here, what? 0. The velocity here is what? You have some velocity here, right? So you have, if distance is huge, you have some sort of profile, right? So you have a complicated velocity field between that, if the distance is significant. But I can always manufacture that so that that distance is 0.1 millimeter, very, very tiny. In that case, what happens? The velocity here is what? Again, 0. The velocity here is what? If I say the inner diameter is Ri, right? This is Ri. And the outer diameter is Ro. What's the velocity here? So velocity here is 0. Velocity here?
Omega?
Is V, capital V, which is what? If you have a rotating wheel, what was the velocity on the wheel?
Omega over radius? Or omega times radius?
Omega times radius. So you get omega times radius. What's the velocity of this wheel? What's the radius of that wheel? Ro. It's not Ri. It's Ro. So you have velocity there is omega Ro. And the velocity at the surface is what? 0. So for that, look at it. You get a profile. The velocities are here, and the velocity 0 here, so you have a linear. Why linear? Newtonian. The assumption. If you put honey or ketchup there, it's not necessarily linear. It's just a complicated line. You see that? Now, if I ask you, this is a quiz waiver, it's not a written waiver. If I ask you, find the value of torque required to keep this thing rotating. Because if you don't apply torque, what happens? There is a shear stress coming from this field that causes, damping the outer cylinder down. And if you don't apply torque, it's going to stop eventually. Right? So you have to apply torque in order to keep it with constant rotation. Find the relation between torque and that omega. Yeah.
Wouldn't you find the force from, let's see here, force from stress times area, and then you would put it into your torque equation, which is R times F, force times sine theta, correct? And which the sine theta would be 0.
Right. Overall correct. So email quiz waiver. Overall correct. Sometimes the quiz waiver, because we are going to have a lot of quiz waivers. The quiz waivers are just to explain. You don't need to get actual number, right? But the midterm waiver is coming. We're not to that point. So as he said, all I need to do is to find the shear stress on the outer cylinder developed that causes that to be on the inner cylinder, and then multiply that by area to get the force. And that force is the force acting on the outside of, you see, all the shear stress that applying a tangential force here. And if I integrate all of those, then I get multiplied by this moment arm. What's the moment arm? Ri. Then I get the torque required on the inner cylinder to keep it in equilibrium. So that's what I'm going to do. So first, let's find the value of the shear stress here, down, at this surface, because this is what I'm going to integrate in order to just like this to get the force on the surface, and then multiply by moment arm to get the torque, right? So what's the value of shear stress at this surface? If assuming Newtonian, all right, here top at the surface of cylinder is equal to mu du dy is equal to mu is just the dynamic viscosity of fluid, right? Do we have it? No. The entire purpose of that is to find the mu times. What can I write for du dy according to this shape that I'm writing here? You say this is my delta small. Let's call this delta, the distance between these two. Let's call that the small value, call it t. The delta. T is equal to delta. It's very small, t. Call it t, thickness, right? So what can I write for the velocity gradient? You can say u times u at the next point. What's the u at the next point? What's the u here? What's the velocity here?
It's the same.
Huh?
It's going to be the same.
Yeah, but what's the value of velocity here?
You have to write that.
Omega RO.
Omega RO, you just wrote it. Omega RO minus the velocity here at this surface. What's the velocity at the surface of cylinder?
0.
0 divided by y at the next point. What's the y here? Minus, y at the next point minus that y is equal to what? T. The distance in the y. What's the distance in the y? The delta y. The thickness, right? So you get that relation. Tau is equal to, if I simplify that, just get rid of that 0. Tau is equal to mu 0 omega RO divided by T. But look, this just gives you the shear stress at the surface of this cylinder, everywhere on the surface of this cylinder. If I want to integrate all this tiny shear stress, what should I multiply that shear stress by to get the force there?
The area?
The area, right? So if I multiply that value by the area, I'm going to write it here. If I multiply that, mu 0 omega RO divided by T. By the area, what's the area of the surface of cylinder? You see, I'm not talking about bottom or top, just the surface. No, pi 2 square is the area of the top or bottom. It's the surface area. You see
Each
that?
times the circumference, so.
The circumference times height, right? Which is what? H times, what's the circumference?
2 pi r O.
Okay, what are Ri or Ro?
We're on the outer circle, right?
We are on the inner circle.
So
We're trying to find
R.
tau here. You see the tau on the inner circle. So 2 pi r I. So that is what? That is force. The entire animal is force.
Where are we applying the torque? I'm confused.
We are applying, we are rotating the outer cylinder with a constant velocity, and we keep the inner cylinder constant, not rotating. But the torque is measured on the inner cylinder. So the outer cylinder is rotated by machinery, so obviously they apply torque to rotate it. But the torque is probably variable, but the speed is constant. On the inner cylinder is constant, we just measure the torque. So all we do right now is to measure everything on the inner cylinder, right? Okay? So that's a force. That's a force what? That's the entire force on the surface of the inner cylinder. But am I going to find the force? I'm not measuring the force on the surface of cylinder. What am I measuring? The torque. The torque. So how can I convert this force to the torque on the center of the inner cylinder? So this is the force. Look, this is the force on the surface. This is the summation of all this dF on the surface. How can I convert this surface force to the torque on the center of that?
Multiplied by r, right?
Yeah, multiplied by Ri. Who said that? Who is it? One quiz there, one quiz. So this you multiply that, so you get torque required to keep the inner cylinder at a constant position, or M is equal to this F multiplied by Ri, which is equal to mu0 omega Ro divided by T times H 2P Ri, and if you multiply that by Ri, you get Ri squared. Look at this relation. I can rearrange this relation in this form. Right here. I can rearrange that relation and solve it for viscosity. So if you solve that for viscosity, what do you get? You get mu is equal to multiply both sides by T, so you get M times T, right? Divided by omega R0 H 2 pi Ri squared. So you can make it like bring 2 pi here. So mt divided by 2 pi omega R0 H Ri squared. Yeah.
How come we neglected the surface, the bottom surface area of the cylinder?
That's the
I can
meter
understand
waiver.
it.
That's the meter waiver.
Okay.
Your book is not including that because it's a little bit complicated. This is page, if you go to your book, if you have your book, this is page number 23. And this equation is in your book. Page 23. And this equation is in your book. And this equation is simplified. Why? In fact, you get a quiz waiver for asking that question. Very important question. He said that if I go to workshop and manufacture this, precision manufacturing, there's got to be a bottom here, right? Otherwise, this fluid will just drop. And this bottom, again, you have some contact, right? So in fact, you have some contact here, and there is some viscosity here, and we'll add up to that equation. How can we just simply neglect it? The answer to that is you don't neglect it. In the real equation that you're going to find next, which is not in your book. Why is not in your book? Because the purpose of that book is, when you just explain to you, is just make things simple, right? Obviously, the author could definitely solve that himself, and he has more advanced problem compared to that. But for just matter of explaining things to you, it just makes it simple, right? So we ignore the bottom and top, which only consider the surface friction. All right? Okay. Now, if I measure torque, how do you measure torque? This sensor right here. You measure torque, you have thickness, all the dimensions, you have the omega, and then you get fluid viscosity. If the torque is just too much, what do? You reduce the velocity, right? Otherwise, your machine will break down, okay? Now, before we go to the actual meter waiver, I want to give you a first meter waiver, and that is this problem. You lubricate right here. For this, you only have 4 minutes. And then we go to second meter waiver. So this is your incline, and you have a block. The dimension, this is the ceiling block. I don't want to write it here. I want to make it too big, but this block is a cubic block with all sides equal to D. D, the perfectly cubic block. So here is the thing. I lubricate the surface of incline. So let's say there is going to be a tiny value of fluid. Why? Because I lubricated it. It's viscosity mu. And I assume it's Newtonian. It's not honey, it's not ketchup, it's just water, right? It's some sort of like Newtonian engine oil. And here is what I do. I have a mechanism that I can crank this up or down, so I can change the incline angle. And at some point, I observe that the velocity this is going down is a constant velocity. All right? So I'll put this weight here. Let's say its mass is m. The size dimensions are given. And I see that it's accelerating, right? So I go to my mechanism and I decrease the angle. Slowly, and at some point you see this is slowly going down the incline with a constant velocity. Right? It's not accelerating, constant velocity. How can I get viscosity using this mechanism? You see, we are trying to find different way of measuring viscosity. One way was the metal sheet, the other way was cylinder. The other way is to make the incline, right? And then lubricate. This is not accurate. The most accurate one is that one. We are going to even make it more accurate. And then change the angle theta such that it goes down with constant velocity.
Tan inverse theta.
How can you find the relation for mu versus all these parameters? So I'll give you a couple of minutes and then I'll solve it myself. If you can solve it to get a meter waiver, come to the whiteboard, solve it, and then you get a meter waiver. Otherwise, I solve it myself and you don't get a meter waiver. We can assume that the thickness of lubrication layer is delta. So that thickness is delta. is tangent theta or tangent theta?
Yeah.
Okay, we'll see. We'll see. We'll see. Well, you remember we have 5-step algorithm. Every time we solve a problem, we have 5-step algorithm, right? Vector status. So if you memorize something, sometimes it may work, sometimes it may not. But if you follow the 5-step, it always works. So system, which one should I choose as my system? The block itself. Look at it. Just a block, right? So if I create the FTD for the block, that's my block. Right? And I want to exaggerate, so this is the surface of incline. And so obviously this is my wall, and that's my fluid. Right? So you have fluid going fast here, and then the velocity. What's the velocity of fluid here? What's the velocity of the lubrication at the wall?
0.
Just 0. What's the velocity at just interface between the fluid? So that's a fluid, right? What's the velocity here at the interface of block and fluid?
V constant.
V of the block. V of the block. And we know that the V of the block is constant. Why? Because I can rotate that thing up so it doesn't accelerate. At some point it goes just constant velocity. So I can do that. So look, and from 0 to block, and assume that this thickness, I call this thickness delta. So from here to here is delta, right? Assuming this is very small. Is it good assumption?
Mm-hmm.
Yeah, it's lubrication. You see, for lubrication, that value is actually very, very small. You just lubricate, right? That value is very small. So what do I get if this value is small and this fluid is Newtonian? What do I get for velocity profile? Linear. Right? So what can I write for the gradient of velocity here? So the shear is equal to what? Newtonian. Mu du dy. For that, I can approximate that. Mu times, what's the change in the velocity? V block minus 0, because the velocity at surface is 0, divided by delta. That's your top. Well, this is just the shear stress at this wall. And you can approximate the same thing if this is in equilibrium. If you take this as your system and write equation of equilibrium, you have the same shear here and here, right? One shear here, the resistance goes this way, and the same thing here. So that's actually could be shear on the top. But it's just shear stress. In order to get the resultant force, resultant frictional force on the block, what should I multiply this by? The surface area of this block. You see this block is like that. You see that? What's the surface area of that? E squared. So you multiply that, you say the frictional force coming from the lubricated fluid is this value, mu v block, divided by delta times E squared. But you may ask, well, how can I measure the force on the block? Here I had a little fixture that could measure the torque because the inner cylinder was fixed. How can I measure the velocity? How can I measure the torque force here on this block? This block is free to go down. The answer is, yeah, you just do 5 steps again. If you take this system, you get that. FBD, you get this friction right here. F friction, right? F friction. And then you have a normal force. And then you have nothing else on this block except the gravity, the weight. There you go, mg. And what is this angle? Just beta, right? That's equal You see, if this angle is this, in this triangle, this theta, this is 90, 90 minus theta, therefore this theta. So that angle is theta. So if I write the equation of equilibrium for this guy, what do I get in the x direction? In the x. I get some force in x0. What do I get? F mg sine theta positive
Minus friction.
minus friction, which is what? Minus
All of
friction,
that.
which is mu times
V
v
delta.
over delta d squared, right? Times minus friction is equal to 0. So look at it. I solve that for mu. So I have what? I have mu is equal to mg sine theta. Now I have everything available. I don't need to measure the force. I have theta, I have mg, so mg sine theta multiplied by delta divided by v e squared. I have everything measured. I have the mass of the block, I have the angle of incline, I have the thickness of lubrication, right? I can measure the velocity. How can you measure the velocity in that? Using the camera, right? Have you heard about image processing algorithm like tracking objects? You can track, you can put a tracker on the block, and then you can track it in the image. And depending on the snapshot, you can find the time difference between the image and the location, and you can find velocity using image processing. So you can have the velocity, you have the dimension, everything. You can define the velocity. Is this accurate? Look, we mentioned the thickness of the lubrication. The thickness of lubrication is not really accurate. Once again, just like plate. You can't just say exactly how much that thickness is. The most accurate one is this one because we fixed the thickness, the rotating cylinder. Now I was going to give you another meter, a waiver, but I'm not going to do that. We're going to do it next class. Okay? I'll put some videos there. We also talk about videos